All right, let's talk about one of the biggest, most mind-bending ideas out there, infinity. But we're not just looking at one version of it. Today, we're diving into a tale of two infinities. One that's been the absolute bedrock of modern physics for a century, and a radical new idea that comes at the problem from the complete opposite direction. Let's get into it.
So what's the big problem we're trying to solve here? Well, in the quantum world, the number of things, particles, isn't fixed at all. They can just pop into existence and then vanish in an instant. So how on earth do you build a theory that can actually handle that kind of beautiful chaos?
And this isn't just some philosophical thought experiment. I mean, this is the fundamental challenge of quantum physics. When the number of players in the game is always changing, your standard math just breaks. You need a completely new kind of toolkit to even begin wrestling with this idea of infinity.
Okay, so enter player one, Fock space. This was developed way back in 1932 by the physicist Vladimir Fock, and it has been the standard, go-to tool for quantum field theory ever since. For nearly 100 years, this is how physicists have managed to tame that chaos. The absolute best way to get your head around Fock space is to picture an infinite library. No, seriously. Picture a library with a ground floor, a first floor, a second, and so on, just stretching up forever. And each floor is specially designed to describe a system with a very specific number of particles. So here's the key, right? Each floor is its own self-contained world. The ground floor, that represents the vacuum, 0 particles, nothing. The first floor describes all the possible states for exactly 1 particle. The second floor handles all the states for exactly 2 particles, and this structure just keeps on going, floor by floor, all the way up to infinity. Now, you're probably wondering, how do we get between these floors? Well, physicists came up with these incredible mathematical elevators. You've got a creation operator that lets you add a particle to the system, which takes you up 1 floor in our library, and then you have an annihilation operator that does the exact opposite. It removes a particle and takes you down a floor. Simple as that. And of course, this brilliant library has rules. It recognizes 2 basic kinds of particles. First, you've got bosons. Think of them as the social butterflies. You can cram as many of them as you want into the very same state. But then you have fermions. They're the loners. An exclusion principle says only 1 is allowed per state, period. And these different behaviors are built right into the math of how those elevators work. Okay, so that's Fock space. Now, let's totally flip the script and look at our second framework. This is the theory of infinity, or TII. And instead of starting with 0 particles and building your way up, TII starts from a much more, philosophical place. This quote really gets to the heart of the theory of infinity, and it's a pretty profound idea. It suggests that infinity isn't some limit we're trying to reach. Instead, it's the fundamental raw material of the universe itself. The reality we see all around us is just what emerges when you carve out finite, stable structures from this formless, infinite potential. So if Fock space is a library you build from the ground up, TOI is like a sculptor who starts with a single infinite block of marble. The goal isn't to add more stuff. The goal is to carve away, to impose structure and definition on this limitless raw material until a recognizable, finite shape finally appears. So what are the sculptor's tools? According to this theory, there are 2 main ones. First, you have symmetry operations, which act like the chisel. They generate structure and create form. And second, you have invariants. These are stable mathematical quantities that act as a quality check, making sure the shape you're carving is actually stable and sealed off from the rest of that infinite marble. The theory even proposes a specific recipe for this whole sculpting process. It's called the Amanda engine. You can think of it as a 4-step creative loop. You start with a little nudge, an impulse. Then you calculate its effects. Then, and this is the critical part, you audit the result to make sure it's stable and follows the rules. And finally, you refine and repeat the loop, carving out more and more complex structures with every single pass. So we have our 2 big ideas, the library and the sculpture. One builds up, the other carves down. Let's put them side by side now and really see just how deep these differences go. This table really just lays it all out. Fock space starts with nothing and builds up this huge library of particle floors. TOI starts with everything and carves down a tower of reality. In Fock space, symmetry is a property of the system. It leads to things like conservation laws. But in TOI, symmetry is the engine itself. It's what creates structure in the first place. The whole mechanism is different. Algebraic elevators versus an algorithmic loop.
And this, right here, this gets to the absolute heart of it. For Fock space, infinity is potential. You can always add one more floor to the library, but any real estate you describe is finite. It lives on a specific floor. For TOI, infinity is ontological. It's the actual substance of reality, the very stuff that finite things are made of. It's a huge difference in thinking.
So how does our sculptor know they're carving correctly? Well, the process uses these audits, checking the structure against very specific mathematical benchmarks. For example, one of those benchmarks is this famous number, pi squared over 6. You can think of it as a precise measurement the sculptor has to hit to make sure their creation is stable and won't just crumble back into that infinite mark.
So, okay, we have two radically different views on infinity. But why does comparing these abstract ideas actually matter? I mean, what can we really learn from putting a physicist's library next to a philosopher's sculpture?
Well, what's truly fascinating is that even though they come from opposite ends of the universe, conceptually speaking, they have some deep structural DNA in common. Both frameworks organize complexity into layers or levels. Both use the principle of symmetry as a fundamental guide. And both of them rely on these stable, unchanging quantities invariants to define the rules of the game and make sure everything holds together. At the end of the day, this is about more than just a philosophical debate. The tools we invent to think about infinity literally define the boundaries of what we can create. And this doesn't just apply to understanding the universe, but to building our future. Think about AI systems that have to handle a constantly changing, nearly infinite stream of information. That's a problem that sounds remarkably similar to counting quantum particles, right? The way we frame infinity shapes our solutions. Our conceptual tools are evolving. The real question is, what new realities will we build with them next?